Alright, let's begin. So for this video, we're going to be talking about inputtables. Inputtables have the request registry and deregistry, as well as the scene registration and deregistration, as all other examples do. These are the scene registration and deregistration is passed through to the associated input register and deregister through the attorney. So whenever the input register or input deregister is processed by the whenever these are processed by the request broker, they will be, which is again, request broker is at the start of the update. Whenever it's processed here, that will determine when it enters and exits the scene. Beyond that, we have a storage strut to store all the necessary information for each key, which includes the key, what state we care about, the registration deregistration request, its current registration state, and its iterator location inside the key managers, which we will discuss later. Outside of that, the inputtables have a map for all the active and inactive inputs. Because we do not know how many inputtable requests the users are going to make, we cannot preload every single key combination. So instead, whenever the user requests a registration, we'll be creating the storage data for each key pair on the fly. So the user will request a key and a key state. If they have not requested it in the past, they will be creating a new key state, which will be stored in a strut, pushed into the map, and then we will be registering that through the submit request in the scene attorney to be processed by the registration broker. When the user requests for that thing to be deregistered, rather than just getting rid of it, instead we are going to be pushing it from the active storage into the inactive storage. So now, because it's been pushed into the inactive storage, the next time the user requests that same key pair, we can look inside our inactive storage for it, and if we find it, we can push that into the active, and that saves us time creating new things and not having to delete them later. Beyond that, when it's time to register and deregister, we push it all the way up to the input manager. The input manager is responsible for a map of Azure keys and key managers. It does not directly manage the inputtables. So what the input manager has is it has its own map of Azure keys. So whenever the user inputs a key, because again, we can't afford to make a key manager for every single key on runtime. That would be a waste if the user never uses it. So instead, we check to see if the user has requested this key in the past. If the user has not requested it, we just make a new key manager. And regardless of if they requested it in the past or not, once we get past this if statement, we register the inputtable to that new key. And then deregistering, we'll call the deregister inputtable from the key manager as well. When it's time to process elements, which is done in the scene, it's done after collisions but before the alarms. When it's time to do that, we will be going through all of our key managers and checking the current key state. And then after that, or when it's time to delete the input manager, we will be deleting all of our key managers here. Onto the key managers. So the key managers have the registration and deregistration for an inputtable. It also has the check key call to determine what state the key is in. We also have the processing of each of the associated lists. And then we have 4 lists, one for each state. So key manager has four different states it could be in. So when the user passes in the inputtable and the key state, based on the key state, it determines which list we push into. And whenever we push into a list, we always pass the iterator back to the inputtable so that we can have fast delete, so that we can have fast delete for when the user wants to deregister. So when the user deregisters their given key state inputtable pair, we will be erasing after we get the iterator from that pair. So that allows us to do a fast access delete. For the keys, for checking the key state, we have to check to see if the key is down. If the key is down, we check to see if it's the first frame it's down. And if it's the first frame, we do the processing of all the press commands. And then after we do that, regardless of if it's the first frame the key is down or if the key's been down for more than one frame, we process all the down key requests. And then we have the inverse for the key release. We check to see if it's the first frame that the key has been released. If so, we flip around our flag tests so that it will not do the key release for more than one frame. We've processed all the release keys, and whether it's the first frame the key was released or multiple frames after, we will process all the up key requests as well. Processing the requests will take the associated key command, so either key press, down, release, or up, and it's going to be passed through from the attorney into that spot so that the user can then call the associated variation. So the key manager itself, something important to note, because the key manager doesn't have any news, it does not have any destructor. The destructor is the default one. The key manager never created anything. The input manager created all the key managers, so the input manager is responsible for cleaning that up. And then the inputtables created all of the registration requests, so it is responsible for deleting them from the active and inactive storages. The last thing to talk about, for the frigate, we have registration, deregistration alternating, similar to how I tested the alarmable and drawables. So as I hold the L key, you can see eventually the frigate will stop rotating, even though I'm still holding that key down, and then it will continue rotating once the other alarm goes off before it stops again. If I were to press the space key, we can see space is pressed and then space is released. I press it, I hold it, nothing changes. I release it, and then it's released. And that is everything.